Picture this, a future where our grandchildren celebrate birthdays on Mars, where scientists conduct research in the oceans of Europa, and where trade routes stretch between planets like celestial highways. It's a vision that feels almost within our grasp, a testament to human ingenuity and our unyielding drive to explore. But beneath the surface of this breathtaking expansion lies a hidden problem, one so fundamental we rarely stop to consider it. Time itself begins to unravel. On Earth, we take for granted that a second is a second, that noon means the same thing in Tokyo as it does in Toronto. But out there, among the stars, every planet spins at its own rhythm, every moon follows its own beat. Without a universal way to keep time, our interplanetary civilization could fracture before it even begins. That's where the quantum clock enters the story, not as some abstract scientific curiosity, but as the silent guardian of our cosmic future. This isn't just about building a better clock, it's about reimagining timekeeping from the ground up, using the strange and wonderful rules of quantum mechanics to create a standard so precise, so unshakable, that it could sync human activity across the solar system and beyond. Think about what's at stake: communication delays, navigation errors, even the simple act of scheduling a call between Earth and a research base on Titan could become logistical nightmares if our clocks can't agree. The quantum clock offers a solution, but it's one that pushes the boundaries of physics, engineering, and our very understanding of reality. In this video, we're going to journey into the heart of this revolutionary idea. We'll explore why humanity's next great leap into space depends on solving this silent crisis of time, how quantum clocks work their magic, and what it will take to weave them into the fabric of our interplanetary society. From the mind-bending science that makes them possible to the very human stories they'll one day enable, this is a tale of ambition, innovation, and the relentless pursuit of sync in a universe that never stands still. So settle in, we're about to uncover how a device no bigger than your palm could one day become the heartbeat of human civilization, binding us together across the vast and lonely expanses of space. So if time is this fragile thread holding our civilization together, what happens when we start stretching that thread across the solar system? The answer lies in one of the most profound and counterintuitive discoveries in all of science: Einstein's theory of relativity. It tells us that time is not the rigid, universal constant we perceive in our daily lives. Instead, it's a fluid, malleable fabric that bends and stretches under the influence of gravity and motion. This phenomenon is called time dilation, and it's not just theoretical, it's a measurable reality that becomes a monumental engineering problem the moment we leave Earth. Think of it like this: imagine two identical, perfectly synchronized clocks. You leave one on your desk here on Earth, and you send the other on a journey to Mars. Even if you could instantly bring that Martian clock back, you'd find they no longer match. The clock that went to Mars would be behind, having ticked just a tiny bit slower during its trip. This isn't a mechanical error, it's the universe itself running at a different speed. The reason is twofold. First, Mars has less gravity than Earth. According to general relativity, the stronger the gravitational field, the more time slows down. So a clock on Earth, deep in our planet's gravity well, ticks slower than a clock on Mars. Second, if the clock is moving at high speed like on a spaceship traveling between planets, special relativity tells us that time slows down for the moving object relative to a stationary one. Now, these differences are incredibly small on human timescales. We're talking about gaining or losing milliseconds over many years. But in our hyper-synchronized, digitally driven world, those milliseconds matter. We already have to account for this on Earth. The atomic clocks in the GPS satellites orbiting our planet, for example, run faster than identical clocks on the ground because they're in a weaker gravitational field. If engineers didn't deliberately program their software to correct for this relativistic effect, the entire GPS network would become useless, accumulating errors of several miles per day. That's for satellites just 20,000 kilometers away. Now, scale that problem up to the interplanetary level. A financial transaction between Earth and a Martian colony, meant to be instantaneous, could be logged at the wrong time, creating accounting chaos. A critical software update for a life support system on a Titan base might arrive with its instructions scrambled because the sending and receiving computers disagree on what now means. Most critically, precision navigation becomes a nightmare. Piloting a spacecraft to a precise orbital insertion around Jupiter requires knowing your position and velocity with insane accuracy. If your onboard clock is out of sync with the navigation network's clock by even a fraction of a second, you could miss your target by thousands of kilometers. Over the decades and centuries of interplanetary civilization, these tiny errors don't just add up, they multiply, threatening to desynchronize our species across the void. Our current atomic clocks, as brilliant as they are, simply can't maintain the coherence needed to overcome the universe's own warping of time. This fundamental flaw in our cosmic timekeeping is the precise reason we need to look beyond atoms to the spooky, predictable, and utterly stable world of the quantum. So if our current clocks are doomed to drift apart in the cosmic dance of relativity, what could possibly keep them in sync? The answer lies in a technology that sounds like it's straight out of science fiction, but is rapidly becoming a laboratory reality: the quantum clock. To understand how revolutionary this is, we first need to appreciate the genius of the clocks we already have. Our best atomic clocks are marvels of precision. They work by using lasers to measure the unwavering, natural vibration of atoms, like cesium or rubidium. Think of an atom as a tiny, perfect pendulum that swings at a rate that never, ever changes. It's this reliable ticking that defines our international standard for a second. These clocks are so accurate they'd only lose a single second every 100 million years. For life on Earth, that's more than enough. But for a multi-planet civilization, it's not even close, because while the atoms inside each individual clock are perfect, the clocks themselves are isolated, standalone devices. They're like 1,000 brilliant musicians, each playing their own flawless rhythm, but from separate soundproof rooms. They have no way to listen to each other, to harmonize, to become an orchestra. And when you place these isolated clocks on different worlds, each experiencing its own unique gravitational pull and velocity, relativity ensures they will immediately fall out of sync. Their perfection is their limitation. They are islands of precision in a relativistic sea. A quantum clock shatters this isolation by harnessing two of the most mind-bending phenomena in physics: superposition and entanglement. Let's break that down without the jargon. Superposition is the idea that a quantum particle, like an atom or an electron, can exist in multiple states at once. It's not just vibrating, it's vibrating in a blend of all possible ways it could vibrate. This isn't a lack of knowledge, it's a fundamental property. A quantum clock uses this blurriness to create a much more sensitive and stable measurement of time's passage. But the real game changer is entanglement. This is the magic that turns a collection of individual musicians into a symphony. Einstein famously called it spooky action at a distance. When two particles become entangled, they lose their individual identities and become linked in a single, shared quantum state. What happens to one instantly influences the other, no matter how far apart they are, whether they're across a lab or across the solar system. This connection happens faster than the speed of light, not because information is traveling, but because the particles are, in a very real sense, not separate at all. Now apply this to timekeeping. Imagine we have a network of quantum clocks. We don't just synchronize them at the start of their mission and hope for the best. We entangle the particles inside them. This means the clock on Earth and the clock on Mars are no longer two independent devices. They are two parts of a single, unified system. Their ticks are fundamentally linked. If relativity tries to slow down time for the Martian clock, the entangled connection to its Earth-bound partner acts as a constant correction, a cosmic feedback loop that maintains their sync. They aren't just comparing notes, they are sharing the same existence. It's the difference between two friends trying to clap in unison over a laggy video call versus two dancers connected by a rod, moving as one perfectly coordinated unit. Pioneers in this field, like Dr. Junyi and his team at the National Institute of Standards and Technology, are already demonstrating this breathtaking potential. They've built optical lattice clocks that use strontium atoms and principles of quantum mechanics to achieve such staggering accuracy that they would not gain or lose a second for 15 billion years, longer than the current age of the universe. This isn't just an incremental improvement, it's a leap into an entirely new class of precision. And it's this level of stability, combined with the binding power of entanglement, that transforms a science experiment into the foundational technology for a connected humanity. It provides a common heartbeat, a universal now, that can be shared from the sun-scorched plains of Mercury to the icy rings of Saturn, ensuring that our future among the stars is built on a schedule we can all agree on. The real magic, the true revolution of this technology, lies in exploiting that spooky connection. Entanglement is the secret ingredient that transforms a collection of supremely accurate but isolated clocks into a single, unified system. To grasp why this is so critical, consider the mundane but vital act of updating a clock. Right now, if Mission Control on Earth wanted to synchronize a clock on a rover exploring the dunes of Mars, they'd have to send a radio signal. That signal, traveling at the universal speed limit of light, takes anywhere from 4 to 24 minutes just for a one-way trip. You send the time update, wait up to 20 minutes for it to arrive, and then wait another 20 minutes to get a confirmation signal back. By the time the process is complete, the information is nearly an hour old. You're not synchronizing to the present, you're synchronizing to the past. For any system requiring split-second coordination like landing a spacecraft, managing a power grid, or executing a high-frequency trade, this delay is utterly crippling. An entangled network of quantum clocks completely sidesteps this problem. Because the particles within the clocks are intrinsically linked, they don't need to send a signal to communicate. The synchronization isn't a message that travels, it's a state of being that is shared. If a gravitational shift near Jupiter causes the local clock's internal particles to vibrate a fraction slower, the entangled particles in the clock on Earth would reflect that change instantaneously. There is no lag, no delay, no light speed barrier to overcome. It's as if the entire network is breathing in perfect unison, with each clock acting as a single node in a distributed, galaxy-spanning consciousness for time. This allows for a continuous, real-time correction that our current methods can't even dream of. Groundbreaking experiments are already proving this principle on a planetary scale. Teams led by physicists like Anton Zeilinger at the University of Vienna and Jian Y. Pan in China have successfully demonstrated quantum entanglement over distances exceeding 1,200 kilometers, using satellites to beam entangled photons between ground stations. They've shown that this spooky action not only survives over vast distances, but can be used to create perfectly correlated keys for unbreakable encryption, a technology known as quantum key distribution. This isn't a laboratory parlor trick. It's a robust field test of the very mechanics that would underpin an interplanetary internet and timing network. Scaling this up to link Earth with Mars is a monumental engineering challenge, certainly, but it is no longer a question of physics. The universe permits this connection. Our job is to build the tools to harness it. Envisioning the final system reveals an engineering marvel of almost incomprehensible complexity and beauty. We wouldn't rely on a single pair of clocks, but a resilient web of them. Orbiting around every planet and moon we inhabit would be satellites housing these quantum timekeepers, each one entangled with multiple partners across the solar system. This redundancy creates a stable, fault-tolerant network. If one clock fails or is temporarily obscured by a planetary body, the others maintain the sync, constantly cross-checking and calibrating against each other. The system would be self-healing, a living fabric of time that can't be easily torn. Deploying and maintaining this network would become one of the primary tasks of interplanetary civilization, a continuous project as vital as maintaining highways or power lines is for us today. It would require a new class of engineers, quantum network specialists, whose job is to tend to this celestial metronome, ensuring the beat that guides our ships and connects our communities never falters. This isn't just about knowing what time it is. It's about creating the temporal infrastructure upon which everything else, our economy, our science, and our shared human experience will be built. This ability to sidestep the speed of light is the most profound advantage of quantum timekeeping. We've established that entanglement creates an instantaneous link, but what does that actually look like in practice for a mission controller or a ship's pilot? Let's paint a picture of a critical operation, like docking a massive supply vessel with a rotating space station orbiting Mars. With our current technology, the pilot on final approach would be flying blind. Their view of the station and their own navigational data would be minutes out of date. Any command they send to adjust their thrusters would be based on where the station was, not where it is. It would be like trying to park a car by only looking in a rear-view mirror that shows you what was behind you 20 minutes ago. The margin for catastrophic error is immense. Now equip both the station and the ship with clocks that are part of the same entangled network. They aren't sending video feeds or velocity vectors back and forth faster than light. That's still impossible. Instead, they are operating from a shared, constantly updated understanding of the universal time standard. The ship's computer knows with absolute certainty what time it is for the station's computer right now. This allows them to pre-agree on a meticulously choreographed docking sequence, a timeline of events measured in microseconds. At a pre-entangled, precisely agreed-upon moment, the station extends its docking clamps. At that exact same instant, as defined by their shared quantum time, the ship fires its stabilizer thrusters. They are executing a dance where the music, the flow of time itself, is perfectly in sync for both partners, even though they are separated by millions of kilometers. The delay is rendered irrelevant because they never needed to communicate during the maneuver. They simply followed the score, a score written in the unbreakable rhythm of their entangled particles. This isn't just theory. The foundational work is being validated right now in orbit around our own planet. Quantum communication experts like those leading the MISHA satellite project in China have already demonstrated the core principle. They've used entangled photons beamed between a satellite and ground stations to perform what's known as quantum key distribution. creating encryption keys that are secure from any eavesdropper. The success of these missions proves that we can generate, maintain, and detect quantum entanglement over the vast and turbulent distances of space, overcoming atmospheric interference and orbital velocities. Each of these experiments is a crucial stepping stone, testing the resilience of the quantum link in the harsh environment where it will one day need to operate. They are building the confidence that this spooky action can be engineered into a reliable, rugged tool, moving it from the pristine isolation of a physics lab to the practical, vibration-filled reality of a deep space probe. This progress signals that the biggest hurdles are no longer questions of fundamental physics, but of engineering, investment, and international will to construct the first interplanetary network that truly operates as one. But before a single quantum clock can be launched or a single particle entangled, humanity faces a more fundamental challenge, one of pure coordination. We must agree on what time it actually is out there. Think of it this way: having the world's most perfectly synchronized orchestra is meaningless if the musicians can't agree on what sheet music to play. On Earth, we solved this problem centuries in the making with Coordinated Universal Time, or UTC. It's the grand compromise that syncs our wall clocks, our computers, and our financial markets, creating a single, authoritative timeline for our planet. Space has no such standard, and the moment we step off our home world, our familiar timekeeping system begins to distort and break down. Establishing a universal time standard for space isn't just an academic exercise, it's the foundational legal and technical framework upon which everything else depends. This new standard must accomplish something UTC never had to. It must be decoupled from the rotating, gravity-heavy environment of Earth itself. It needs to account for the fact that a second on Mars is not the same duration as a second on Earth when measured against the backdrop of the universe. The relentless pull of relativity guarantees that. So, what do we use as our unchanging reference point, our fixed North Star for the solar system? One of the most compelling proposals from leading astrophysicists and organizations like the International Astronomical Union is to base this new interplanetary time on the solar system's barycenter, the common center of mass around which the Sun, planets, and all other objects gravitationally balance. Imagine the solar system not as the Sun sitting statically in the center with planets whirling around it, but as a complex dance where every participant, even the giant Jupiter, tugs on the others. The barycenter is the precise, calculated point at which this entire cosmic dance is balanced. It's often located just outside the surface of the Sun, wobbling slightly as planets move. This point isn't tied to the gravity well of any single world, making it the ideal, neutral anchor for a solar system time. Adopting a barycentric coordinate time, or TCB, would mean that every clock on every planet and spacecraft could convert its local, relativistically warped time into this universal standard. A scientist on a moon of Neptune and an engineer in an asteroid belt mining operation would both be able to reference TCB to know exactly what time a signal was sent from the other, untangling the knots created by light speed delay and time dilation. This conversion would be handled by sophisticated software, a kind of universal translator for time, using precise models of planetary orbits and gravitation. Locking in this standard is the critical first step, the essential act of diplomacy and science that must precede the hardware. It's the agreement that allows a clock on Mercury and a clock on Pluto to have a meaningful conversation, ensuring that when we finally weave that web of entangled quantum clocks, they'll all be singing the same song from the same hymnal. Designing a clock that remains stable within the controlled environment of a laboratory is one thing. but building one that can survive the violent, unforgiving expanse of space is an engineering challenge of a completely different magnitude. The void between planets is a place of brutal extremes, a searing inferno when bathed in unfiltered sunlight, and a flash-frozen wasteland when cast into shadow. It's flooded with relentless radiation that can scramble delicate electronics and filled with microscopic debris traveling at velocities faster than a bullet. A quantum clock, with its exquisitely sensitive components, must not only function in this hellscape but must do so with unwavering precision, becoming the most reliable piece of hardware we have ever launched. This demands a radical shift in design philosophy. On Earth, scientists can use large, complex systems of lasers, vacuum pumps, and cooling units that sprawl across an entire optical table, all carefully isolated from vibrations and temperature swings. For space, every component must be miniaturized, hardened, and made incredibly power efficient, all while performing to a standard that makes our best atomic clocks seem crude by comparison. The core of these space-worthy quantum clocks will likely rely on one of two leading technologies, each with its own advantages in the fight against environmental chaos. The first approach uses trapped ions, individual atoms held perfectly still in a vacuum by electromagnetic fields. Their isolated nature makes them fantastic sensors for time, as they are less prone to collide with other atoms and disturb their rhythm. The second, and perhaps more promising for long-term stability, is the optical lattice clock. This method uses thousands of atoms, not just one, caught in a crisscrossing pattern of laser beams, a kind of light cage. This allows scientists to take an average of all their vibrations, cancelling out individual errors and creating a collective signal of breathtaking smoothness and stability. To protect these delicate quantum processes, the clock's internal world must be a fortress. Specially designed sapphire cavities can house the atoms, providing exceptional thermal stability and shielding. Every circuit, every laser diode must be radiation hardened, a process that essentially pre-bakes components to make them resistant to the high-energy particles that would quickly degrade ordinary electronics. And just as NASA builds its Mars rovers with redundant systems for critical functions, 2 computers, multiple radios, a deep space quantum clock will need layers of built-in redundancy. Imagine multiple, independent ion traps or optical lattices within a single unit, all cross-checking each other. If one system begins to drift or fail, the others can vote it out of the network, maintaining the integrity of the time signal without a single hiccup. This monumental work is already moving from whiteboard concepts to tangible prototypes. Aerospace giants like Honeywell, who have already developed remarkably precise atomic clocks for terrestrial and near-Earth use, are now collaborating with research institutions to push into the quantum realm. Their goal is to shrink these systems down to the size of a shoebox while making them robust enough to withstand the violent shaking of a rocket launch and then operate flawlessly for decades without any possibility of physical repair. They are the unsung heroes of this endeavor, the engineers and material scientists translating the ethereal laws of quantum physics into solid, reliable, and launch-ready hardware. This isn't just delicate lab equipment anymore. It's the rugged, self-sufficient backbone of the future network, built to keep the beat for centuries amidst the silent, chaotic beauty of the cosmos. Building this universal time standard requires more than just flawless hardware. It demands a physical presence, a network of these quantum sentinels planted firmly on every world we dare to call a second home. A single master clock, no matter how perfect, would become a single point of catastrophic failure. The goal is resilience, creating a distributed web of timekeeping so that the loss of any one node is a minor hiccup, not a civilization-ending event. This means we won't just have a quantum clock on Mars. We'll need an entire constellation of them, woven into the very infrastructure of our off-world existence. Imagine the red planet decades from now. The first clock might be installed at the primary landing base, perhaps inside a radiation-shielded lab module. But that's just the beginning. Another would be positioned at a major mining outpost in Valles Marineris. A third would orbit the planet aboard a space station serving as a transportation hub. These nodes wouldn't operate in isolation. They'd be linked together across the Martian surface and through its thin atmosphere using a system of quantum repeaters. These aren't simple signal boosters. They are specialized devices that can receive a fragile quantum state, like entanglement, and faithfully pass it along to the next node without destroying its delicate properties. This creates a planetary intranet of time, a local network that keeps all of Mars in perfect sync with itself before that synchronized time is then entangled with the wider solar system. The same intricate process would unfold on Europa, with clocks housed in submarines exploring its subsurface ocean and in surface habitats glued to its icy crust, all linked to an orbital gateway. Deploying this infrastructure will be one of the primary objectives of the next great wave of space exploration, a mission profile as vital as searching for water or building habitats. We can already see the blueprint in projects like NASA's Artemis program, which plans to establish a sustained lunar presence. The first interplanetary quantum clocks won't be launched on dedicated missions. They'll be critical payloads aboard the ships that are already scheduled to carry astronauts and supplies. Picture a SpaceX Starship, its cargo bay filled with habitat materials and scientific gear, also containing a hardened, refrigerator-sized module housing a pre-calibrated quantum clock. Upon landing, a specialized team would devote their first days to activating and installing this priceless instrument, treating it with the same care and priority as setting up life support. These initial deployments will be painstakingly slow, hands-on work, akin to the early days of building the International Space Station module by module. The vision extends far beyond the Moon and Mars. This same installation process will repeat itself across the solar system, adapted for each unique and brutal environment. On Mercury, a clock would need to be buried deep beneath the regolith to survive the extreme temperature swings between its scorching days and frigid nights. On a moon like Titan, with its thick atmosphere and hydrocarbon lakes, the clock might be housed in a floating platform, its quantum components kept stable against the cold and atmospheric pressure. Each new deployment is a monumental achievement in adaptive engineering, pushing our technology to survive in places that seem actively hostile to precision. The timeline for this rollout stretches across decades, even centuries, a continuous project of cosmic infrastructure that grows in lockstep with human expansion itself. It's a rolling wave of synchronization, ensuring that wherever humanity plants its flag, it also plants a heartbeat that is instantly, seamlessly connected to home. Even the most perfect network of entangled quantum clocks would be useless without a brain to manage it, a layer of intelligence sophisticated enough to conduct this cosmic orchestra. Think of each individual clock as a virtuoso musician, technically flawless but needing guidance. The gravitational pull of a passing moon, a slight drift in a laser's frequency, the microscopic expansion of metal from a temperature shift, countless variables threaten to introduce tiny errors. Left uncorrected, these minuscule drifts would accumulate, creating a cacophony of conflicting times. This is where artificial intelligence enters the stage, not as a replacement for the physics, but as its essential partner. We need algorithms that don't just process data, but that learn, predict, and conduct. The core challenge these AI systems must solve is the mind-bending complexity of a dynamic solar system. The network isn't static, it's a swirling dance of planets, moons, and spacecraft, all moving at different velocities and experiencing unique gravitational forces. A clock on a moon of Jupiter, for instance, is subjected to a constantly shifting gravitational field as it orbits the gas giant, which itself orbits the Sun. The time dilation affecting that clock is a fluid, ever-changing equation. An AI conductor would ingest a torrent of real-time data from a suite of sensors co-located with each clock. High-precision gravimeters, accelerometers, and thermometers constantly measuring its local environment. It wouldn't just react to changes, it would build a profoundly accurate model of the solar system's dynamics and learn to anticipate them. It could predict that in 12 hours, as a moon reaches the periapsis of its elliptical orbit, the gravitational stress will peak, and it can preemptively apply a tiny, corrective adjustment to the clock's output to compensate. This transforms timekeeping from a passive measurement into an active, intelligent process. The pioneering work being done in adaptive systems at places like MIT's Computer Science and Artificial Intelligence Laboratory and Google AI provides a thrilling glimpse into this future. Researchers there are developing machine learning models that can manage incredibly complex, non-linear systems, from predicting traffic flow in a megacity to optimizing the performance of a nuclear fusion reactor. These systems excel at finding patterns in chaos and making thousands of micro-adjustments per second to maintain stability. Applying this to a solar system time network would involve creating a hierarchy of one master conductor AI might oversee the entire solar system, ensuring the Barycentric time standard remains pure, while subordinate section leader IS manage each planetary domain, the Martian network, the Jovian network handling local corrections and only reporting significant deviations upstream. This distributed intelligence makes the system robust and scalable. This immense power and responsibility immediately brings us to the most critical design requirement: security. A system that forms the temporal backbone of human civilization is a target of unimaginable value. Tampering with it could be more destructive than any weapon. It could silently desynchronize navigation to cause ship collisions, disrupt interplanetary markets by creating arbitrage opportunities through time manipulation, or even hold a colony's infrastructure for ransom by threatening to plunge it into temporal isolation. Therefore, the AI must be designed from the ground up to be not just smart but paranoid. Its algorithms would need to be encrypted and running on hardened, fault-tolerant hardware. Every command, every adjustment, would be cryptographically signed and logged on an immutable blockchain-like ledger, creating an audit trail that stretches across the solar system. The AI would constantly be on the lookout for anomalies that signal an attack, a clock reporting a change that defies the laws of physics, or a series of adjustments originating from an unauthorized source. It would have the authority to quarantine suspicious nodes, isolating them from the network to protect the whole. In this endless, silent battle, the AI is both the conductor and the guardian, ensuring the music of time plays on, secure and true. Building a network of such immense importance means we must also build it to be impervious to attack. The very entanglement that creates an unbreakable sync also provides the key to its defense through a revolutionary technology known as quantum key distribution, or QKD. Think of it this way: if the quantum clock network is the central nervous system of our interplanetary civilization, then QKD is its immune system, constantly on patrol for any foreign intrusion. This isn't a software patch or a firewall added after the fact. security is woven directly into the fundamental physics of the system, making it not just highly secure, but inherently unhackable by conventional means. The genius of QKD lies in its ability to turn the act of spying into a self-announcing event. In traditional encryption, two parties exchange a digital key to lock and unlock their messages. A sophisticated hacker could intercept and copy this key without either party knowing, allowing them to silently decrypt all future communications. Quantum key distribution uses entangled particles to create that key. Because these particles are linked, measuring the state of one instantly affects its partner. So, if a third party tries to eavesdrop on the key exchange by measuring the particles themselves, they inevitably collapse the quantum state. This action doesn't just fail to steal the key, it fundamentally alters it, leaving clear, detectable anomalies in the data that alert the legitimate users to the breach. It's the equivalent of a thief trying to steal a shadow. The very act of grabbing for it changes its shape and gives them away. The system can then immediately discard that compromised key and generate a new one, all before any sensitive time data is ever transmitted. We already have a spectacular proof of concept for this technology operating right now in Earth's orbit, China's MISHUS satellite. Launched in 2016, MISHUS isn't just a theory, it's a working prototype that has shattered distance records for secure quantum communication. In a landmark experiment, the satellite generated entangled photon pairs and beamed them down to two ground stations separated by over 1,200 kilometers. Despite the photons traveling through the turbulent atmosphere, they remained entangled. The team then used these photons to perform QKD, distributing secure keys between the stations and enabling the world's first intercontinental, quantum-secured video call. The success of MISHUS is a resounding validation that the core technology can not only survive the rigors of launch and space, but can also perform its delicate quantum magic across the vast distances we'll face between planets. It moves quantum security from the laboratory to the realm of practical engineering, providing a blueprint for the secure nodes we'll need at every outpost and relay station. Integrating this level of security directly into the timekeeping network transforms its entire nature. Each quantum clock becomes more than a timepiece. It becomes a trusted, certified node in an unbreakable chain of custody for information. Before a clock even reports its time data, the QKD system first establishes a secure channel with its entangled partner. Only once that channel is verified to be free of eavesdroppers does it transmit the incredibly sensitive timing pulse. This process happens continuously, creating a rolling, ever-changing encryption key that is used once and then discarded. For a hacker trying to disrupt the network, the attack surface is virtually non-existent. They cannot simply jam a signal or inject a false one because any attempt to read or manipulate the quantum channel corrupts it. They cannot break the encryption because the key is never transmitted in a classical way. It is manifested simultaneously at both ends of the link through the spooky connection of entanglement. The only way to attack such a system is to physically possess and tamper with a clock itself, a threat that necessitates extreme physical security at each deployment site but renders remote, cyber-based attacks completely useless. This creates a foundation of trust that extends far beyond mere seconds and milliseconds. Consider the implications for an interplanetary banking system, where a transaction worth billions must be time-stamped with absolute certainty to prevent fraud or double spending. Or for military operations, where orders must be executed across light minutes of space with the confidence that they haven't been altered or spoofed by an adversary. A secure time signal authenticates every digital action, providing an irrefutable when that is just as crucial as the who and what. It allows us to build legal frameworks, economic systems, and governance models that can function with integrity across the solar system, ensuring that a contract signed on Ceres is as binding as one signed in London. By baking security into the fabric of time itself, we aren't just protecting data, we are protecting the very notion of agreement and coordinated action, enabling a dispersed humanity to function as a single, cohesive, and trustworthy civilization. This transformation in navigation is nothing short of a paradigm shift, moving us from celestial dead reckoning to a dynamic, real-time positioning system for the entire solar system. For centuries, space travel has relied on a method that would feel familiar to ancient mariners, taking sightings of known stars and planets to triangulate a position. A probe headed for Pluto, for instance, must periodically turn its cameras back towards Earth to image known stars against the background, painstakingly calculating its trajectory and then firing its thrusters in a series of corrective burns. This process is slow, consumes precious fuel, and is inherently reactive. You only know you've gone off course after you've already done so. Quantum clocks rewrite this entire process by turning time into the ultimate coordinate. Imagine a future spacecraft, the Odyssey, departing for the moons of Jupiter. Instead of staring backwards at the stars, its navigation computer is constantly listening. It's tuned into the solar system's quantum time network, receiving perfectly synchronized pulses from entangled clocks on Earth, in orbit around Mars, and at a relay station in the asteroid belt. Each pulse is time-stamped with exquisite precision. The Odyssey's own onboard quantum clock measures the infinitesimal differences in the arrival times of these pulses. Because it knows the exact location of each transmitter in the network and the exact time each signal was sent, it can calculate its own position in three-dimensional space relative to them with centimeter-level accuracy in real time. It's no longer navigating by looking at static landmarks. It's navigating by feeling the precise rhythm of the universe's heartbeat. The practical benefits of this are staggering. Mission planners can shift from conservative, fuel-guzzling trajectories to ultra-efficient, continuous thrust pathways. A ship can make tiny, constant adjustments to its course instead of waiting months to execute a single, massive, and risky correction burn. This saves an enormous amount of propellant, which in turn allows for heavier scientific payloads, more shielding for crewed missions, or simply longer mission durations. It dramatically reduces the weeks of silence during critical maneuvers when a spacecraft is unable to communicate its status to Earth. Most importantly, it turns navigation from a ground-controlled operation into an autonomous process. The crew of the Odyssey isn't waiting for instructions from mission control, a conversation that could have a 90-minute round-trip delay by the time they reach Jupiter. They have a live, updating map of the solar system on their bridge, giving them the situational awareness to navigate hazards like asteroid fields or orbital debris with the confidence of a pilot flying in clear skies. This vision is already in its nascent testing phase. NASA's Deep Space Atomic Clock mission, which concluded in 2021, was a critical first step. It wasn't a quantum clock, but it was the most stable atomic clock ever flown in space, designed to test the very principle of autonomous, time-based navigation. For 2 years, it orbited Earth, demonstrating that such a clock could maintain its precision in the space environment. Its success proved that spacecraft could generate their own ultra-precise navigation signals, a capability that will be essential when light-speed delay makes real-time guidance from Earth impossible. The quantum clock is the logical, revolutionary successor to this technology. It takes the stability demonstrated by the Deep Space Atomic Clock and multiplies it by orders of magnitude, then weaves individual clocks into that unbreakable, entangled web. This isn't just an incremental improvement, it's the key that will unlock the outer solar system, making crewed missions to the icy giants and their fascinating moons not just possible, but almost routine. The risks plummet as precision soars, inviting an era of exploration where the question is no longer if we can go, but simply what we will discover when we arrive. For the men and women living and working on the red sands of Mars or in the pressurized domes of a lunar colony, the abstract miracle of quantum timekeeping translates into the most practical, tangible benefits imaginable. It becomes the invisible glue that holds their daily lives together, transforming a collection of isolated outposts into a cohesive, functioning society. Consider the simple act of starting the workday. On Earth, time zones are a manageable inconvenience, a predictable rolling wave of 9-to-5 schedules. But on a planet like Mars with a soul, its solar day lasting just over 24 hours and 39 minutes, the concept of a day is fundamentally unaligned with Earth's. Without a unified time standard, each individual habitat could theoretically adopt its own arbitrary timekeeping, leading to a chaotic patchwork of schedules. A miner in the Hellas Planitia Basin might be halfway through their sleep cycle when a manufacturing engineer at the North Pole base is starting their morning. Coordinating a simple inter-habitat supply run would become a logistical puzzle. Quantum-entangled clocks eliminate this friction entirely, while settlers would still experience the natural light and dark cycles of their local world. Their official timekeeping for work, communication, and administration would be locked to the solar system's universal standard. This means a team meeting scheduled for 1400 hours solar system time happens at precisely 1400 hours for everyone, from a geologist in a canyon on Mars to a mission controller in Houston. Video calls with loved ones back on Earth, while still subject to a few minutes of light speed delay for the video stream itself, can be scheduled with absolute certainty. There's no confusion about your time versus my time. There is only the time. This shared temporal framework is perhaps most critical for emergencies. If a dust storm cripples a remote research station, the dispatch of an emergency rescue rover and the preparation of a medical bay at the central hub can be coordinated down to the second, with all parties operating from an identical timeline. This precision can mean the difference between a successful evacuation and tragic miscommunication. The need for this standardization becomes even more apparent when we consider worlds with truly bizarre rotations. Take Mercury, for example. Its day, the time it takes to complete a single rotation, is a staggering 176 Earth days long. A traditional 24-hour clock is meaningless there. A human settlement on Mercury would need to invent an entirely new way to structure its society, likely based on work cycles aligned with the extreme temperature shifts between the long day and night. Yet, even there, their unique local calendar and clock would need to be seamlessly convertible to the universal standard. A Mercurian accountant filing a quarterly report to a corporate headquarters on Earth, or a student attending a virtual university lecture streamed from Luna, would rely on that conversion to ensure deadlines are met and classes are joined on time. The quantum network provides the trusted translation layer, allowing for local cultural adaptation while maintaining global interoperability. This harmony finds its most beautiful expression in the deeply human moments that define us. Picture a young girl named Ilara celebrating her 10th birthday inside a habitation module in the Jezero crater on Mars. Her party is scheduled for 1800 hours SST. At that exact moment, as defined by the entangled clock on the wall of her home, a digital frame flickers to life. It displays a live feed from her grandparents' living room on Earth, where they are also observing 1800 hours SST. They sing "Happy Birthday" in unison, their voices slightly out of phase due to the light-speed lag of the audio, but their smiles and the candles on two separate cakes are perfectly synchronized to the same instant in time. This shared experience, this ability to occupy the same now, despite being separated by hundreds of millions of kilometers, fosters a powerful, unbreakable sense of connection. It reinforces that they are not two separate branches of humanity drifting apart, but one family, one culture, stretched across the cosmos yet still bound together by the immutable beat of a shared heartbeat. This daily, lived experience of synchronicity is what transforms the quantum clock from a piece of high technology into a cornerstone of interplanetary culture, a silent guardian of our shared identity. Yet for all its technical perfection, the quantum clock network would ultimately be judged not by its precision, but by its people. Time, after all, is far more than a measurement. It is the very rhythm of human culture, the invisible scaffold upon which we hang our rituals, our work, and our shared identity. The transition from sundials to mechanical clocks didn't just help us be more punctual. It fundamentally reshaped society, enabling the coordination required for global trade, industrial revolutions, and the modern world. The adoption of a unified interplanetary time standard represents a cultural shift of even greater magnitude, one that could either bind our scattered civilization together or become a source of friction between worlds. The most profound benefit of this shared heartbeat is its power to forge a new planetary identity. For the first time in history, a child born in a dome on Mars and a grandparent living in Jakarta would literally be living by the same clock. This shared now provides a powerful psychological tether, a constant reminder that despite the unimaginable physical distances, every human being is participating in the same unfolding moment of cosmic time. It transforms abstract connectivity into a tangible, lived experience. Sociologists studying future colonization, like Dr. Lisa Ruth Rand, often point to the danger of founder effects, where isolated communities can rapidly develop cultural practices and even languages that diverge from their point of origin, potentially leading to misunderstanding and conflict over generations. A universal time standard acts as a powerful counterweight to this drift. It creates a common ground for commerce, law, and media, ensuring that a financial quarter, a legal deadline, or the premiere of a much-anticipated solar system-wide vid series happens at the same instant for everyone, fostering a sense of unified participation in a grand human project. This doesn't mean erasing local culture or rhythms. The most likely and fascinating outcome is the rise of a dual-time society. Just as many people on Earth today operate on both their local time zone and a global standard like UTC for work, future Martians or Titanians would live two temporal lives. Their body clock and daily routines would be synced to the natural light-dark cycle of their local world, the 24.6-hour sol on Mars, or the 16 Earth day-long cycle of daylight on Titan. This local time would govern sleep schedules, meal times, and community festivals tied to the alien seasons. But superimposed on this would be solar system time, the immutable pulse from the quantum network. SST would govern all interplanetary affairs, the opening of the markets, the timing of long-distance communications, the departure of transport ships, and diplomatic summits held via quantum-secured links. This bifurcation wouldn't be a burden. It would be a natural adaptation, a way to be both a proud citizen of your local world and a participating member of a solar system-wide civilization. However, this transition will not be without its debates and dissent. A significant philosophical question lies at the heart of this project. Are we imposing an Earth-centric system on the cosmos, and in doing so, are we perpetuating a kind of temporal colonialism? Some futurists and cultural theorists argue that by basing our universal time on the solar system's barycenter, we are still using an Earth-born concept of timekeeping. A truly alien intelligence, they suggest, might perceive time in a completely different way, perhaps as a non-linear or multi-dimensional fabric. While we are not dealing with aliens, we are dealing with new branches of humanity who may, over centuries, develop radically different perspectives. Imposing a single time standard from the beginning could be seen as stifling this cultural evolution. There may be strong movements on some colonies, especially those farthest from Earth or with the most independent ideologies, to develop their own unique timekeeping conventions that better reflect their world's environment and their community's values. These debates will extend into the most intimate aspects of life, reshaping our most cherished traditions. How do you celebrate New Year's Eve when your planet doesn't orbit the Sun at the same pace as Earth? Do you mark the occasion at the stroke of midnight SST, creating a galaxy-wide party, or do you invent a new holiday tied to your local calendar? How are work weeks structured on a world with a different rotational period, and how does that interact with a solar system-wide economy that operates on a fixed clock? Sleep scientists will be at the forefront, working to help colonists adapt their circadian rhythms to alien days while still needing to be alert for critical calls scheduled on universal time. The solutions will be a fascinating blend of biology, technology, and culture, perhaps involving tailored lighting in habitats, strategic use of melatonin, and the widespread adoption of personal AI assistants that seamlessly manage an individual's complex dual-time schedule. This cultural layer reveals that the quantum clock is more than a tool. It is the catalyst for the next great chapter in human social evolution, challenging us to redefine what it means to be together when we are so far apart. The same unshakable precision that guides ships and connects families will become the invisible engine of the first true interplanetary economy. Here on Earth, the entire architecture of global finance, from high-frequency stock trades to international wire transfers, rests on the bedrock of perfectly synchronized time. A discrepancy of even a single millisecond can mean the difference between profit and catastrophic loss. Now, project that system across the vast and delayed expanse of our solar system, and the need for a universal clock transforms from a technical advantage into an absolute economic necessity. Consider the challenge of trade. A mining corporation on Ceres, the largest object in the asteroid belt, extracts a fortune in platinum group metals. A manufacturer in orbit around Mars needs that raw material to build new spacecraft. Today, finalizing that deal would be a logistical nightmare. The initial purchase order might take over 15 minutes to reach Ceres. The confirmation and contract could take another 15 minutes to come back. The actual transfer of payment, handled by banks on Earth, would be subject to its own series of delays. A simple transaction could take over an hour to complete, a lifetime in economic terms where market prices for such valuable commodities can fluctuate wildly. This isn't just an inconvenience, it's a fundamental barrier to a fluid, efficient market. Quantum entangled timekeeping vaporizes this barrier, because all financial institutions across the solar system operate on the same, trusted universal timeline. They can pre-program smart contracts. These are self-executing agreements with the terms of the deal written directly into code. The moment the cargo ship from Ceres docks with the Martian manufacturer's station and its sensors confirm the delivery of the ore, that event is time-stamped with an unforgeable quantum-certified time. This timestamp automatically triggers the release of payment from the manufacturer's escrow account to the mining company's bank. The entire transaction verification, settlement, and transfer of funds happens instantly and automatically the nanosecond the goods are received. There are no waiting periods, no settlement delays, and no room for dispute over when the deal was completed. This creates a level of trust and efficiency that allows capital and resources to flow through the solar system with the same frictionless ease we experience online today. This reliability unlocks entirely new financial instruments and services. Banks could offer interplanetary loans with interest rates calculated down to the second across any number of time zones and planetary rotations, with absolute certainty that their calculations are correct. Insurance companies could underwrite policies for spacecraft and off-world infrastructure with premiums that dynamically adjust in real time based on risk data time-stamped from across the network. Venture capital firms on Earth could invest in startups on Enceladus with the confidence that their equity stakes and shareholder agreements are governed by a temporally precise legal framework. Companies like SpaceX, with its vision for a fleet of starships creating a supply chain between worlds, and Blue Origin, with its focus on industrializing near-Earth space, are not just building rockets, they are laying the groundwork for these markets. Their success and the trillions of dollars in potential wealth they seek to create is wholly dependent on having a financial system that can operate faster than the speed of light, a paradox made possible only by the spooky, instantaneous correlation of quantum clocks. This economic engine promises to democratize access to the solar system's resources. A small-time investor on Earth could use a trading platform to buy a fractional share of a water ice mining operation on Europa, receiving micro-dividends calculated on a per-second basis from the moment their purchase is confirmed. The ability to timestamp every step of a supply chain from extraction to refining to transport to sale with unhackable certainty creates unprecedented transparency, attracting investment and stabilizing the value of off-world commodities. This robust, hyper-efficient economic layer is what will ultimately fund the next wave of exploration and settlement, creating a virtuous cycle where profit fuels progress, and progress opens new frontiers for profit. Yet this entire intricate and powerful web of interplanetary commerce dangles by a single, fragile thread: the continued, flawless operation of the quantum clocks themselves. For all their revolutionary potential, these devices are not magical. They are machines, and machines in the brutal environment of space face a constant, relentless assault that threatens to plunge the entire economy back into the dark ages of delay and distrust. While the potential of entangled clocks is breathtaking, the universe itself seems almost designed to disrupt this delicate quantum connection over the vast distances between planets. This fragility is the single greatest obstacle we face. Entanglement isn't a robust, physical cable you can simply string from Earth to Mars. It's more like a whisper-thin strand of spider silk, exquisitely sensitive to the slightest interference. The very fabric of space itself is a chaotic and noisy environment, filled with forces that constantly threaten to decohere our entangled particles, to collapse their delicate linked state back into separate, ordinary matter. This decoherence comes from everywhere. The endless hail of cosmic radiation, high-energy protons and atomic nuclei screaming across the void can slam into a satellite and disrupt its sensitive quantum hardware. The subtle but persistent tug of gravitational waves, ripples in spacetime caused by colossal events like merging black holes, can minutely warp the environment around our particles, enough to break their spooky bond. Even the faint whisper of the cosmic microwave background radiation, the leftover heat from the Big Bang that permeates all of space, adds a constant, low-level static to the system. Over a few hundred kilometers in Earth orbit, we can shield against much of this, but over the hundreds of millions of kilometers to Mars, these effects accumulate, posing a relentless and unprecedented engineering challenge. The most promising solution to this problem lies in a remarkable piece of technology called a quantum repeater. You can think of a quantum repeater not as a simple amplifier, which would destroy the quantum state by measuring it, but as a skilled and trustworthy translator. A standard signal booster reads a fading message and shouts a new, louder copy. A quantum repeater does something far more subtle. It receives the fragile quantum state, the entanglement itself, and without ever fully measuring or collapsing it, faithfully generates a fresh, new entangled pair further down the line, effectively extending the range of the connection in a series of hops. It's the equivalent of a relay runner passing the baton without breaking stride, ensuring the original team's effort continues seamlessly. Building a network of these repeaters that can span interplanetary distances is one of the most ambitious goals in modern physics. Current research is focused on proving the concept on ever larger scales. The International Space Station has served as a critical testbed for this. Experiments like NAS, a cold atom lab, have successfully created Bose-Einstein condensates, a state of matter where atoms behave as a single quantum entity in the microgravity of orbit. This research isn't about entanglement directly, but it's a vital step in learning how to control and manipulate quantum systems in the unique environment of space, where factors like gravity are minimized. Other projects are testing the fundamental limits of how far we can transmit entangled photons from satellites to ground stations, gathering invaluable data on how the atmosphere and empty space affect the quantum link. Yet, even as we make progress, fundamental questions remain. Quantum mechanics itself may impose theoretical limits on the range or fidelity of entanglement over such epic scales. Some theories suggest that the expansion of the universe itself, the gradual stretching of space-time, could eventually impose a maximum distance beyond which entanglement cannot be maintained, though that horizon is far beyond our current solar system ambitions. The challenge is immense, but history shows us that such monumental hurdles are often the catalysts for our greatest leaps forward. The struggle to overcome signal loss in early transatlantic telegraph cables led to fundamental breakthroughs in electrical engineering. The need to calculate artillery trajectories birthed the modern computer. In the same way, the desperate need to protect a quantum whisper across millions of kilometers will inevitably force us to discover new physics, new materials, and new engineering principles we can scarcely imagine today, turning our greatest weakness into our most profound strength. Even with a flawless network of quantum clocks humming in perfect sync across the solar system, a profound and deeply personal challenge remains untouched. The machines may agree on what time it is, but the human body, governed by the unyielding laws of relativity, will experience time in a profoundly different way. This isn't a problem of synchronization. It's a problem of perception, a biological reality that forces us to confront a startling truth. The universal now is a comforting illusion, and our very experience of life's passage is relative. This concept is famously illustrated by the twin paradox, a thought experiment that has leaped from the pages of physics textbooks into the realm of impending reality. Imagine two identical twins. One remains here on Earth, living a comfortable life in a steady gravitational field. The other embarks on a journey to a massive planet like Jupiter or on a high-speed voyage to a distant star system. Due to the combined effects of velocity and gravity described by Einstein, time literally passes more slowly for the traveling twin. When the astronaut twin returns after what felt to them like a few years, they might step back onto Earth to find their sibling has aged decades. Their clocks, if they were perfectly entangled quantum devices, would still agree on the exact time down to the picosecond, having corrected for the dilation. But the biological clocks of the twins, their wrinkles, their memories, the very number of heartbeats they've experienced would tell two irreconcilably different stories. This isn't just a theoretical puzzle for physicists like Brian Greene, who has eloquently explored its implications. It's a looming social and philosophical dilemma for a multi-planetary species. A construction worker who signs a 5-year contract to build orbital infrastructure around Saturn will return to an Earth that has moved on without them in a very literal sense. Their children might be older than they are, their cultural references outdated, their entire world changed. This creates a new form of time zone shock, one measured not in hours but in years of lived experience. The very concept of a shared human timeline begins to fray at the edges. What does retirement planning look like when a decade of work for you means 30 years of market fluctuation back on Earth? How do you maintain a marriage or a friendship across a gulf of relative time that is constantly widening? These questions force us to re-examine the most fundamental building blocks of society: law, ownership, and even identity. Consider inheritance. If an individual spends significant time traveling between high-gravity and low-gravity worlds, whose time dictates when they come of age or when their assets are distributed upon their death? Does a will executed in Earth's time frame hold legal weight for an heir who has lived most of their life on a world where time crawls? We might see the emergence of relativistic lawyers specializing in untangling these chronological knots, and financial instruments like time dilation insurance to protect the assets of those whose careers require them to step outside the mainstream flow of time. This human layer reveals the ultimate limit of our technological ambition. We can build a network that syncs every clock in the solar system, creating a flawless coordinate of clock time. But we cannot build a device that syncs human biology or lived experience. This is the poignant reminder that for all our ingenuity, we remain physical beings subject to the universe's deepest rules. The project then evolves from a purely technical challenge into a profoundly human one. It becomes about building a society adaptable enough to accommodate these different rates of existence, to find ways to keep families and cultures connected even when their members are literally living their lives at different speeds. The quantum clock gives us the tools to coordinate our actions across space, but it is empathy, foresight, and flexible social structures that will allow us to synchronize our hearts. The journey from a stunning laboratory breakthrough to a rugged, space-worthy instrument is a monumental leap, and it's a path currently being forged by a global alliance of scientists, engineers, and visionary agencies. We are no longer just theorizing about quantum clocks. We are actively building and testing them, pushing the boundaries of what's possible both on Earth and in the harsh environment of space. These pioneering projects are the crucial stepping stones, the real-world experiments that are turning a breathtaking concept into an inevitable technology. Perhaps the most significant milestone in this journey was NASA's Deep Space Atomic Clock mission. While it wasn't a full-fledged quantum clock utilizing entanglement, it was a revolutionary leap forward and a critical proof of concept. Launched in 2019, this mission wasn't about keeping time for Earth. Its entire purpose was to test the core principle of autonomous, time-based navigation for spacecraft. At its heart was a super-stable mercury ion atomic clock, a technology far more precise than the rubidium clocks used in GPS satellites. For over 2 years, it orbited our planet, and the results were staggering. It demonstrated a stability that was 50 times better than any existing space-ready clock, losing only about 1 second every 10 million years. More importantly, it proved that such a delicate instrument could survive the violence of a rocket launch and then operate with unwavering precision in the microgravity and radiation of space. This mission wasn't the final destination. It was the critical first step onto the interplanetary highway, validating that the foundational technology for this new navigation paradigm could not only work but thrive beyond our atmosphere. Simultaneously, on the ground, researchers are tackling the other half of the equation, creating and maintaining the quantum connections themselves. Across Europe, a consortium of universities and tech companies is running extraordinary experiments, sending entangled particles racing through hundreds of kilometers of underground fiber optic cables. These aren't simple data transfers. They are attempts to preserve that fragile, spooky link across real-world distances, battling against the inevitable signal loss and environmental interference that occurs in glass fibers. Each successful experiment, each time they verify that the particles at the end of the cable are still linked, brings us closer to understanding how to build the quantum repeaters we'll need to chain together between planets. This work is painstaking and happens largely out of the public eye, but it is just as vital as the flashy space missions, laying the hidden groundwork for the network's nervous system. The driving forces behind this global effort are a fascinating mix of public institutions and private ambition. The National Institute of Standards and Technology, or NIST, in the United States remains a world leader with physicists like Dr. John Yi pushing optical lattice clocks to levels of precision that defy belief, clocks so accurate they would not gain or lose a second for longer than the current age of the universe. Their work defines the very standard we are striving to achieve, but they are no longer alone in this race. Private companies, sensing both a massive technological advantage and an enormous future market, are entering the field with fierce determination. Companies like Cold Quanta and Sandbox AQR are developing commercial-grade quantum sensors and clocks, working to shrink the sprawling, room-sized laboratory setups into hardened, rack-mounted units that could eventually be installed on a satellite or a lunar lander. This blend of pure research and commercial drive is accelerating progress at an unprecedented rate, ensuring that the technology doesn't languish in academia but is rapidly engineered for real-world application. So, what does the timeline from these prototypes to a fully operational interplanetary network actually look like? Based on the current trajectory, we can map out a plausible, if ambitious, future. The next decade, through the 2030s, will likely focus on extended lunar operations. The upcoming Artemis missions and the planned Lunar Gateway space station provide the perfect testing ground. We can expect to see the first operational, non-entangled but highly stable atomic clocks, successors to the deep space clock, installed on the Gateway and perhaps at the planned Artemis base camp. These will be used to practice and refine the techniques for autonomous lunar navigation, working out the kinks just a short light second away from Earth. The following decade, the 2040s, is when the quantum leap should truly begin. This is when we can anticipate the first demonstrations of entanglement over interplanetary distances, likely between Earth and a relay satellite at a Lagrange point or directly with a clock on the Martian surface. These will be short-duration, carefully orchestrated experiments, but they will prove the physics on the scale that matters. This progression suggests that a rudimentary but functional solar system time network could be a reality by the latter half of this century, perhaps around the 2080s. It won't be the resilient, redundant web we ultimately envision, but rather a critical backbone linking Earth, Mars, and key transportation hubs. This timeline is not guaranteed. It hinges on sustained funding, international cooperation, and overcoming the immense engineering hurdles of decoherence we discussed. But the pace of current research, the convergence of interest from national space agencies and private corporations, and the sheer necessity of the technology for our future in space all point towards one undeniable conclusion. The ticking of a universal quantum clock is not a question of if, but a question of when. And that when is rushing towards us faster than many realize. Based on the incredible progress we're already witnessing, a realistic timeline for deploying these quantum clock networks begins to take shape, and it's far closer than most people might assume. The first operational nodes won't appear on Mars or at some distant Lagrange point. They'll be installed right next door on the Moon. The upcoming Artemis program provides the perfect, and indeed the only, logical proving ground. Throughout the 2030s, as NASA and its international partners establish a sustained presence on the lunar surface, the priority will be testing and validating the foundational technologies for living and working beyond Earth. This makes the Moon an ideal laboratory for the first generation of space-hardened quantum clocks. We can expect to see them first as critical payloads on uncrewed lunar landers, perhaps by the middle of the decade, tasked with simply surviving the landing and reporting back data. Shortly after, they'll be integrated into the Lunar Gateway Station orbiting the Moon, and eventually housed in the pressurized modules of the Artemis base camp itself. This phased approach allows engineers to work out the kinks, study the effects of the lunar environment on quantum coherence, and develop the operational protocols for maintaining these exquisite machines, all while being just a few light seconds from help. Following this lunar shakedown cruise, the next giant leap will target the red planet. The 2040s are poised to be the decade of Mars, with multiple agencies and private companies targeting crewed missions. These voyages will demand a level of navigational precision that only quantum-enhanced systems can provide, creating a powerful incentive for their deployment. The first Martian quantum clock will likely be part of the initial infrastructure sent ahead of human arrival, perhaps landing in the late 2030s to ensure it is fully calibrated and operational when the first astronauts touch down. This initial node would be a solitary sentinel at first, but its mere presence would mark a historic turning point. It would begin the painstaking work of mapping the precise time dilation effects of Mars's gravity and rotation, creating a rich dataset that will be essential for entangling future clocks. The goal by the end of the 2040s would be to establish a minimal functional network, one primary clock at the main landing site, another on an orbiting support station, and perhaps a mobile unit on a long-range rover, all linked together and beginning the process of establishing a stable link back to Earth. Of course, this entire timeline hinges on overcoming two monumental, non-technical challenges: funding and international will. The development and deployment of this technology will be astronomically expensive, requiring a sustained financial commitment that must survive political cycles and shifting public priorities. A useful comparison can be drawn to the development of the Internet. From the early conceptual work on ARPANET in the 1960s to the world-changing ubiquity of the World Wide Web in the 1990s, the process took over 3 decades and required consistent investment from government defense and research agencies before the private sector could capitalize on it. The quantum clock network faces a similar path. It is a foundational infrastructure project whose full economic benefits won't be realized until long after the initial investment. This requires a unique partnership between visionary government bodies like NASA and the European Space Agency, and deep-pocketed private entities like SpaceX and Blue Origin, who have a direct commercial interest in unlocking the solar system. A failure to secure this funding, or a major political decision to redirect resources away from deep space exploration, could easily delay the entire project by decades. The other great variable is the pace of discovery itself. We are still in the early days of quantum engineering, and a single unexpected breakthrough could dramatically accelerate our progress. A team in a lab somewhere in the world could tomorrow discover a novel material that dramatically reduces decoherence, or a new method for entangling particles that is far more robust over long distances. Conversely, we might encounter a previously unknown fundamental physical limit that throws a wrench in the entire plan, forcing a years-long pivot to a new approach. This is the nature of pioneering research at the very edge of our understanding. The history of technology is littered with both unanticipated leaps forward and frustrating roadblocks. Setting a rigid timeline is therefore a fool's errand. Instead, we should view the coming decades as a window of opportunity, a period where the scientific knowledge, engineering capability, and economic incentive are all aligning to make this future not just possible but probable. The urgency comes from understanding that the sooner we build this temporal backbone, the sooner we can safely and efficiently become a multi-planet species, transforming humanity's future from a precarious single-planet existence into a resilient, solar system-wide civilization. Perhaps the most profound aspect of this entire endeavor is that in our quest to build the perfect clock, we may inadvertently construct the most powerful scientific instrument ever conceived. These quantum timekeepers designed to sync human activity could become our most sensitive detectors for uncovering the universe's deepest secrets, probing realms of physics that have eluded us for centuries. This transforms the project from a monumental feat of engineering into a grand scientific expedition, turning the solar system itself into a laboratory for fundamental discovery. The key lies in their mind-boggling precision. A network of entangled quantum clocks doesn't just measure time, it measures the fabric of space-time itself with a sensitivity we've never before achieved. General relativity has been spectacularly successful, but physicists widely acknowledge it's an incomplete theory. It beautifully describes the cosmos on large scales, but it breaks down at the quantum level, at the heart of black holes, and at the moment of the Big Bang. Unifying gravity with quantum mechanics to form a theory of everything remains the holy grail of modern physics. A solar system-spanning quantum clock array could be the tool that finally provides the experimental data to guide us there. These theories often predict subtle, exotic effects, minute variations in the way time flows or space curves under extreme conditions. These variations are so infinitesimally small that they are completely drowned out by noise in any Earth-bound experiment. But by distributing these exquisitely sensitive clocks across different gravitational environments, from the weak pull of an asteroid to the crushing gravity well of Jupiter, we create a galaxy-sized interferometer. It's like having 1,000 listening posts, each tuned to hear the faintest whisper of new physics in the silent symphony of space. One of the most thrilling possibilities is the direct detection of dark matter. We know this mysterious substance makes up about 85% of all the matter in the universe, yet we have only inferred its existence through its gravitational pull on galaxies. We have no idea what it actually is. Many theories suggest it could be composed of incredibly light, wave-like particles that permeate all of space. As our solar system moves through the galaxy, it might periodically pass through denser streams or clumps of this dark matter. If these particles interact with ordinary matter even a trillionth of a trillionth as much as a neutrino does, they would impart a tiny, shuddering force on everything, including the atoms inside our clocks. This would cause the delicate quantum states of those atoms to vibrate at a specific, detectable frequency. A single clock might miss it, but an entire network would see a coordinated, correlated disturbance sweep across the solar system, a ghostly fingerprint revealing the presence and properties of the invisible stuff that binds the cosmos together. Nobel laureate David Wineland, a pioneer in the field of quantum optics and precision measurement, has often spoken about this potential. He describes these future clocks not as timekeeping devices, but as sensors for the anomalies of the universe. He suggests that by watching for tiny, persistent drifts between clocks in different locations, drifts that cannot be explained by known relativistic effects, we might be measuring something entirely new. We're looking for a discrepancy, Wineland has said, a crack in the otherwise flawless face of our current theories, and that crack is where the light of a deeper understanding gets in. This sentiment is echoed by researchers at the forefront of quantum gravity, who see these clocks as a way to test string theory or loop quantum gravity by looking for evidence that spacetime itself has a discrete, granular structure at the smallest scales, a potential foamy texture to reality that would reveal itself through subtle, quantized steps in how time evolves. This incredible power immediately thrusts us into a new realm of responsibility, raising profound ethical questions that we must confront long before the first interplanetary clock is powered on. Controlling the very definition of time itself and possessing instruments that can literally sense the fabric of reality is a form of power unlike any humanity has ever wielded. It is the ultimate informational advantage. The entity or consortium that operates the primary time standard effectively holds the keys to the entire interplanetary economy, navigation, and communication network. This creates a risk of a temporal monopoly where access to the most precise time could be throttled, taxed, or weaponized. A malicious actor wouldn't need to blow up a clock. They could simply introduce a barely perceptible, systematic drift into the network, enough to slowly desynchronize navigation for a rival corporation's fleet or create arbitrage opportunities in financial markets. The potential for a new form of Cold War, fought not with missiles but with picoseconds, is a very real danger. Furthermore, the scientific discoveries themselves could be destabilizing. What if the clocks detect incontrovertible evidence for a theory that fundamentally rewrites our understanding of physics, such as the existence of extra dimensions or the ability to manipulate spacetime? The knowledge of how to potentially engineer such effects would be concentrated in the hands of the small group of scientists and engineers who built and maintain the network. The ethical imperative for transparency and international oversight becomes paramount. The development and governance of this quantum timing infrastructure cannot be the project of a single nation or a private company. It must be a globally collaborative effort, akin to the International Telecommunication Union or the governance of the Internet's domain name system, but with even greater stakes. We are not just building a tool for coordination. We are building a lens to view the deepest workings of the universe, and we must ensure that the view and the power that comes with it benefits all of humanity. This immense power to define and distribute time itself thrusts us into a complex ethical landscape that we must navigate with foresight and wisdom. The very technology designed to unite humanity could, if mismanaged, become the ultimate instrument of division and control. Imagine a future where the most precise, stable time signal is a commodity owned and operated by a single corporate entity or a dominant nation-state. A colony or spacecraft that cannot afford the licensing fees for this premium time would be forced to rely on a degraded public signal, much slower to correct for relativistic drift. Their navigation would be less precise, their financial transactions would settle more slowly, putting them at a permanent economic disadvantage, and their ability to participate in high-precision scientific research would be limited. This wouldn't just create a digital divide, it would forge a fundamental rift in reality, stratifying civilization into temporal haves and have-nots, where your access to the universal now depends on your wealth or political allegiance. The potential for coercion is staggering. A controlling entity could subtly throttle the time signal to a rival corporation's shipping fleet, causing their autonomous freighters to gradually drift off course and miss critical delivery windows, bankrupting them without firing a shot. They could offer a more precise signal to Allied colonies as a political reward, creating a two-tiered system of interplanetary citizenship. Or, in a more dystopian scenario, they could threaten to disconnect an entire world from the network entirely, effectively plunging it back into a pre-synchronized era of isolation and navigational chaos, holding its population hostage to a temporal siege. This isn't just about minutes and seconds, it's about who gets to participate in the future on an equal footing. Space law scholars like Dr. Elsbeth Maggleton often point to the foundational Outer Space Treaty of 1967, which declares that space is the province of all mankind and is not subject to national appropriation. The principle of equitable access is a cornerstone of international space law. The governance of a solar system time standard must be held to this same ideal, treated not as a proprietary technology but as a public utility, akin to the global positioning system which the United States government provides as a free, open service to the entire world. Preventing this requires proactive, international collaboration built on transparent and inclusive frameworks from the very beginning. We cannot wait until the network is built and then argue over who holds the keys. The safeguards must be engineered into its foundation. One compelling model is the governance of the Internet itself, particularly the role of the Internet Corporation for Assigned Names and Numbers, or ICANN. While imperfect, it demonstrates a multi-stakeholder approach where technical experts, civil society, governments, and private companies all have a voice in the stewardship of a critical global resource. A similar body, perhaps an interplanetary time authority under the auspices of the United Nations Committee on the Peaceful Uses of Outer Space, could be established. Its mandate would be to ensure the neutral, secure, and equitable operation of the timing network, certifying hardware, auditing software for backdoors, and resolving disputes over access. The actual physical infrastructure, the clocks and repeaters, could be funded and deployed by a consortium of nations and private entities, but their operation would be governed by this independent authority, ensuring that no single player can monopolize the flow of time. Furthermore, the software and hardware standards must be open source and non-proprietary. This allows for independent verification by any interested party, from a university research group to a rival corporation, ensuring that the algorithms generating the time signal are functioning as advertised and haven't been subtly altered to introduce bias or vulnerability. This transparency is the bedrock of trust in a system where trust is everything. It transforms the network from a black box controlled by a few into a transparent utility maintained for the benefit of all, a shared heartbeat for a dispersed civilization. By enshrining these principles of equity and oversight now, we can ensure that this profound technology fulfills its highest potential as a tool for unification, rather than becoming the next frontier for conflict and control, safeguarding the most precious resource we have, our shared experience of the present moment. This monumental undertaking, the construction of a temporal backbone for our solar system, cannot be the project of a single nation or a private corporation. Its very nature as a universal utility demands a level of international cooperation rarely seen in human history, a collaborative spirit on par with the building of the International Space Station or the global governance of telecommunications. The ISS stands as a powerful testament to what is possible when nations pool their resources, expertise, and ambition toward a common goal, transforming a symbol of Cold War rivalry into an orbiting beacon of peaceful partnership. This model of shared ownership and operation provides the perfect blueprint for what must come next. Just as no single country could have built the station alone, No single entity can or should be entrusted with the sole responsibility for humanity's shared time. The complexity of this task will likely necessitate the creation of entirely new international bodies, specifically designed to manage this unprecedented infrastructure. We might see the formation of an Interplanetary Time Authority, or ITA, operating under the auspices of the United Nations Committee on the Peaceful Uses of Outer Space. This wouldn't be a symbolic organization. It would require real power and a clear mandate. Its responsibilities would be vast and critical. The ITA would be tasked with certifying the hardware standards for all quantum clocks and repeaters, ensuring that every device deployed from Earth to the Kuiper Belt meets rigorous specifications for performance, security, and interoperability. It would manage the intricate process of deploying and registering new nodes into the network, preventing conflicts and ensuring equitable access. Most importantly, it would act as a neutral arbiter, auditing the network's software for vulnerabilities or backdoors and resolving any disputes that arise over signal priority or alleged temporal manipulation. This level of oversight is not about bureaucracy. It is about building trust on a solar system-wide scale, ensuring that every human settlement, regardless of its origin or affiliation, can rely on the time signal as a neutral, incorruptible constant. The path to such cooperation will undoubtedly be paved with treaties and international agreements, legal frameworks that extend our Earth-bound concepts into the cosmos. These accords would need to explicitly define time as a protected common resource, akin to how the Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies. They would establish clear rules of the road for operating within the network, outlining rights and responsibilities, and creating protocols for dealing with malfunctions, sabotage, or the inevitable discovery of new physics that could impact the standard. The existing International Telecommunication Union, which so successfully manages the radio frequency spectrum on Earth to prevent chaotic interference, offers another powerful model. The ITU's ability to allocate bandwidth fairly and efficiently to nearly 200 member states demonstrates that complex technical coordination on a global scale is not only possible but can be remarkably effective. A similar framework will be essential to manage the spectrum of time, ensuring its stability and availability for all. History has shown us time and again that humanity's greatest achievements often spring from our greatest shared challenges. The threat of climate change, while still a fiercely contested political issue, has nonetheless spurred unprecedented global scientific collaboration and diplomatic efforts, however fraught. The silent, relentless challenge of relativistic desynchronization represents a similar, unifying threat to our future in space, a problem that ignores borders and ideologies. It is a purely physical obstacle that every spacefaring nation and company will eventually face, and its solution offers a tangible, beneficial outcome for every participant. This shared technical necessity could become a powerful catalyst for unity, forging partnerships and fostering a spirit of collaboration that transcends terrestrial politics. By working together to solve this fundamental puzzle, we wouldn't just be building a network of clocks, we would be strengthening the very bonds of our global community, practicing the kind of governance and mutual reliance we will need to thrive among the stars. Yet for all this grand diplomacy and high-level agreement to take root and flourish, it requires a foundation of something far more fundamental: the understanding, engagement, and unwavering support of the public back here on Earth. But none of this technical or diplomatic progress will matter if the people who are supposed to benefit from it don't understand it or, worse, actively fear it. The most elegantly engineered network in the universe will fail if it's met with public skepticism or outright rejection. The history of technology is littered with brilliant innovations that stumbled not on their own complexity, but on the rocky shores of human perception. For quantum clocks to become the trusted heartbeat of our civilization, we must embark on a parallel journey of education and communication, one that starts long before the first interplanetary clock is ever switched on. The challenge is profound because the science involved is so deeply counterintuitive. We're asking people to trust a system based on principles that defy everyday experience: particles that are in two places at once, instantaneous connections across millions of kilometers, and time that flows at different rates depending on where you stand. Without clear, relatable explanations, this can easily be dismissed as magic or, more dangerously, as a form of technological sorcery too complex to be safe. The risk is that the quantum clock network becomes an esoteric tool for elites, a black box whose workings are understood only by a priesthood of physicists and engineers, creating a trust deficit that could be exploited by fearmongers. We saw this play out with nuclear energy. A technology with the potential to provide abundant, carbon-free power became mired in public anxiety, much of it stemming from a failure to demystify the science and engage in honest dialogue about both its benefits and its risks. The lesson is clear: assuming the public will simply embrace a technology because it is advanced is a recipe for failure. The solution lies in a multi-front educational campaign that begins now. We need to integrate these concepts into STEM curricula at the primary and secondary school levels, not as abstract equations but as exciting stories of exploration. Imagine children building simple models of entangled particles or using virtual reality to experience time dilation on a journey to Jupiter. This isn't about creating a generation of quantum physicists. It's about fostering a generation of quantum-literate citizens who feel comfortable with the basic concepts and see them as a natural part of humanity's toolkit. Beyond the classroom, science communicators and museums have a critical role to play. Exhibits that allow visitors to interact with working atomic clocks or demonstrations that visually represent quantum entanglement can bridge the gap between theory and tangible experience, transforming something mysterious into something marvelous. Popular culture, particularly science fiction, will be one of the most powerful tools in our arsenal. For decades, sci-fi has served as a preemptive testing ground for societal reactions to new technologies, from the communicators of Star Trek predicting the cell phone to the ethical dilemmas of artificial intelligence explored in countless films and novels. We need compelling, human-centered stories that show quantum clocks not as cold, impersonal machines, but as the enablers of profound human connection, the technology that allows an explorer on Triton to read a bedtime story to their child on Earth in perfect sync, or that prevents a catastrophe by allowing a fleet of ships to navigate an asteroid field with flawless coordination. By dramatizing the benefits and thoughtfully exploring the potential pitfalls in an engaging narrative, filmmakers and authors can do what technical white papers never can. They can make people feel why this technology matters. Perhaps the most critical element in building public trust will be radical transparency from the scientific and corporate entities developing this technology. This means openly sharing both successes and failures, publishing research findings in accessible formats, and hosting public forums to address concerns. It means creating independent oversight committees with public representatives to audit the network's security and fairness. If a clock on Mars experiences an unexplained glitch or a research team discovers a potential vulnerability in the entanglement process, that information should be disclosed and discussed openly. Attempting to hide problems will only fuel conspiracy theories and erode trust. The goal must be to create a collective sense of ownership over this project, to make it feel like humanity's clock, not the clock of a specific government or corporation. This human factor, the messy, complicated, and emotional process of gaining acceptance, is not a secondary concern to be addressed after the engineering is complete. It is the very foundation upon which our interplanetary future will be built, ensuring that the rhythm that guides us is one we all choose to follow together. Ultimately, this grand project of synchronization is about far more than just scheduling meetings or landing spaceships. It represents a crucial, foundational step in the evolution of our entire species, a key that unlocks our potential to become what astronomers call a Type 2 civilization on the Kardashev scale. This isn't just a sci-fi concept. It's a serious framework for measuring a civilization's technological advancement based on its energy consumption. A Type 1 civilization, which we are slowly and messily approaching, has mastered all the energy available on its home planet. But a Type 2 civilization is something else entirely, a culture that has harnessed the total energy output of its entire star, a feat that requires an unimaginable level of coordination across a solar system. And you simply cannot coordinate the construction of a Dyson swarm or manage the flow of stellar energy without a perfectly synchronized clock. Think about the sheer scale of the engineering required. A Dyson swarm isn't a solid shell around the sun. It's a vast constellation of billions of individual energy-collecting satellites, orbiting in a meticulously choreographed dance to avoid catastrophic collisions and to efficiently beam power to worlds and outposts across the solar system. The precision required for this is beyond anything we've ever attempted. Each satellite's position must be known and adjusted in real time, with thrusters firing in perfect unison based on a shared understanding of now. A timing error of even a millisecond could cause a cascade of navigation corrections, wasting precious fuel or, in a worst-case scenario, leading to a chain reaction of collisions that could turn the swarm into an impassable shell of debris around our star. The quantum clock network provides the essential metronome for this dance, the universal rhythm that allows billions of autonomous systems to operate as a single, cohesive mega-structure. It transforms a chaotic crowd of individual parts into a harmonious orchestra capable of capturing a star's power. This level of synchronicity enables more than just massive power projects. It allows for the emergence of planetary-scale computing. Imagine a computational problem so vast that it requires processors distributed across Mercury, Mars, and the moons of Jupiter to work on it simultaneously. For these disparate systems to function as a single, unified supercomputer, their operations must be synchronized with picosecond precision. A calculation performed on Europa cannot proceed until it receives a data packet from a server on Earth, and that entire transaction is meaningless if the two systems disagree on the order of operations due to relativistic time drift. The entangled clock network eliminates this problem, creating a single, agreed-upon timeline for every processing cycle across the entire solar system. This allows us to pool our computational resources on an interstellar scale, tackling challenges like climate modeling for terraforming, simulating complex astrophysical phenomena, or cracking problems in fundamental physics that are currently far beyond our reach. In this long-term vision, quantum clocks cease to be specialized scientific instruments and become as ubiquitous and essential as the smartphone is today. They would be integrated into the core of every device, every vehicle, every home, and every piece of infrastructure. Your personal communicator would constantly cross-reference its time with the local planetary network, which is in turn entangled with the solar system standard. This isn't for telling the time of day. It's for ensuring that every digital interaction you have, from authorizing a microtransaction to accessing a secure data stream, is authenticated with an unforgeable timestamp. The clock becomes the silent, unseen guardian of trust in a fully digital, interplanetary society, the fundamental layer upon which all other technologies are built. This vision beautifully ties back to our deepest human drive, to explore, to connect, and to elevate our condition. The quantum clock is the tool that allows us to transcend the isolation imposed by the universe's own laws. It is the antidote to the existential loneliness of space, the mechanism that ensures a researcher on a distant icy moon and an artist in a floating city on Venus are both participating in the same continuous moment of human history. It fosters a shared cultural experience, a common rhythm for our civilization, preventing the fragmentation that would inevitably occur if each world drifted into its own separate timeline. Yet for all its promise, we must also soberly consider the alternatives if this technology proves too fragile, too expensive, or too politically fraught to implement. What is Plan B if the quantum dream fails? One fallback could be a much more complex and cumbersome system of predictive modeling. Every clock in the solar system would run independently, and a massive, centralized supercomputer on Earth would run a near-constant simulation of the entire solar system's gravity and motion. It would calculate the predicted time dilation for every single clock and then broadcast correction factors. This is essentially a vastly more complex version of what GPS does today. The problems are obvious. It creates a single point of failure. It's horrendously vulnerable to light speed delay the further out you go, and it requires a staggering amount of energy just to keep the model updated. It's a clumsy, inefficient patch, not a solution. Another, more radical alternative would be to abandon the dream of a universal now altogether and instead design a society that is inherently asynchronous. We would develop new protocols for communication, commerce, and navigation that do not rely on precise simultaneity. Financial transactions might be based on blockchain-like technologies with built-in delay tolerances. Navigation would revert to a more autonomous star sighting method, with ships being self-contained worlds that only sync up with the broader network when absolutely necessary. This path would fundamentally alter the trajectory of human expansion, likely leading to a much more fragmented and isolated civilization where worlds develop independently at a faster rate, perhaps even evolving into separate cultures with vastly different notions of time and connection. While potentially fostering incredible diversity, this future sacrifices the unifying potential of a shared heartbeat, accepting that the vast distances between stars may ultimately mean that humanity's future is not as a single civilization, but as a family of many, forever separated by the relentless and unsynchronized flow of time. Even with the breathtaking potential of quantum clocks, we must confront a sobering possibility. What if the universe itself refuses to cooperate? What if the delicate dance of entanglement proves too fragile to maintain across the immense, radiation-filled voids between planets? It's a scenario that leading physicists take seriously, and it forces us to consider alternative, less elegant but potentially more robust technologies that could serve as a crucial bridge or even a permanent fallback. This pragmatism is not a sign of diminished ambition, but rather a hallmark of mature engineering exploring every avenue to ensure that humanity's expansion into space continues, even if our most revolutionary tool isn't immediately ready. The most direct and well-understood alternative lies in a significant enhancement of our current atomic clock technology. Instead of relying on the spooky connection of entanglement, this approach would double down on isolated precision, building clocks that are so incredibly stable on their own that their drift due to relativity becomes more predictable and therefore more correctable. We're talking about clocks that are an order of magnitude more precise than anything flying today, perhaps based on new elements like ytterbium or highly charged ions, housed in even more robust and self-calibrating systems. The strategy here wouldn't be to prevent desynchronization, but to model it with such exquisite accuracy that we can effectively subtract its effects. Each clock would be accompanied by a sophisticated suite of sensors, high-precision gravimeters, accelerometers, and thermometers, constantly feeding data into an onboard computer running a complex simulation of the local gravitational environment. This computer would calculate, in real time, exactly how much time dilation the clock is experiencing and apply a continuous software correction to its output. It's a brute force method requiring immense computational power and a near-perfect understanding of physics, but it's built on proven, reliable technology. This concept of a correction model is already in use, just on a much smaller scale. The entire global positioning system is a perfect example. The atomic clocks on board GPS satellites are programmed to run slightly faster than their identical counterparts on Earth to compensate for the relativistic effects of their orbital velocity and higher altitude. Engineers pre-calculated this offset and hard-coded it into the system before launch. The challenge for interplanetary travel is that this model can't be pre-calculated. It must be dynamic. A spacecraft on a journey to Saturn will experience a constantly changing gravitational landscape, swinging past planets and diving through varied regions of the Sun's gravity well. Its onboard model must update its corrections thousands of times per second, a task that pushes the limits of current computing but is not beyond the realm of possibility with advancing processor technology. This approach offers a path forward that is less miraculous than quantum entanglement, but one that is arguably more immediately achievable with our current engineering capabilities. Perhaps the most poetic and truly cosmic fallback option looks not to our own ingenious machines, but to the natural timekeepers of the galaxy, pulsars. These incredibly dense, rapidly spinning corpses of massive stars are nature's most perfect metronomes. As they rotate, they emit powerful beams of radiation that sweep across space like a lighthouse. For some pulsars, these rotations are mind-bogglingly consistent, rivaling the stability of our best atomic clocks over long periods. The European Space Agency has already invested significant research into this concept with their ambitious Pulsar project, exploring the feasibility of using these celestial beacons for deep space navigation. The idea is stunningly elegant. A spacecraft would be equipped with an X-ray telescope capable of detecting the rhythmic pulses from a known set of millisecond pulsars. By measuring the precise arrival time of these pulses and comparing them to a pre-loaded catalog of their expected times, the spacecraft's computer could triangulate its position in the solar system with remarkable accuracy, completely independent of any Earth-based system. This method offers a beautiful form of redundancy. It's a navigation system that cannot be hacked, cannot be jammed, and requires no maintenance from humans. It is, in a very real sense, the universe providing a free, eternal service. NASA has already tested preliminary versions of this technology. The famous Voyager probes each carry a golden record with a pulsar map etched onto its surface, providing directions to Earth for any potential finder based on the unique timing signatures of 14 nearby pulsars. More recently, the Station Explorer for X-ray Timing and Navigation Technology, or Sextant, experiment on the International Space Station successfully demonstrated that pulsar-based navigation is viable, using observations of millisecond pulsars to determine the station's position in orbit. While using pulsars for real-time, centimeter-level navigation across the solar system presents enormous technical challenges requiring large, sensitive telescopes and complex timing analysis. It represents a brilliant standalone backup. It's the ultimate Plan B, a silent network of clocks that have been ticking for millions of years and will continue to do so long after our own civilizations have turned to dust. Comparing these options reveals a classic engineering trade-off between elegance and robustness, between revolutionary potential and evolutionary improvement. The quantum clock network is the elegant, integrated, and instantaneous solution, the high-risk, high-reward path that could redefine our relationship with physics itself. Enhanced atomic clocks with relativistic correction are the pragmatic, incremental upgrade, a harder working version of what we already know, demanding more computing power but offering a clearer path from today's technology. Pulsar timing is the passive, natural, and profoundly resilient solution, a slow but utterly dependable method that operates entirely outside of human control. The most likely future involves not a choice between them, but a layered integration of all three. A spacecraft might primarily navigate using its own enhanced atomic clock, constantly cross-checking its calculated position against pulsar observations, and then using brief, precious moments of established quantum entanglement for critical, high-precision maneuvers like a landing sequence. This multi-layered approach creates a navigation and timing system with incredible redundancy, where the failure of any one technology doesn't spell disaster. This pragmatic exploration of alternatives is far from an admission of defeat. It is a testament to human ingenuity. It reminds us that technological progress is rarely a single, straight line to a predetermined destination. It is a branching tree of possibilities, where dead ends in one branch often nourish explosive growth in another. The relentless pursuit of a quantum clock, even if it ultimately proves too challenging for interplanetary distances, will undoubtedly force breakthroughs in laser stability, vacuum technology, and materials science that will directly benefit the enhanced atomic clocks. The work on pulsar navigation drives advancements in X-ray optics and data processing. Every path forward, even those initially viewed as secondary, adds to our collective toolkit and deepens our understanding of the cosmos. This multifaceted effort ensures that our journey to the stars does not hinge on a single, fragile thread of possibility, but is woven from a strong, diverse cable of tested ideas and bold innovations, any one of which could ultimately provide the rhythm that guides us into the future. The quantum clock, in its silent, unwavering precision, represents something far greater than the sum of its atoms and lasers. It is a profound symbol, a testament to a fundamental shift in human ambition. For our entire history, our greatest projects have been about conquering and connecting our world from Roman roads to the internet. But this is different. This is about mastering a dimension itself, not to impose our will upon it, but to harmonize with its deepest laws, to weave a thread of unity through the vast and empty expanses that seek to pull us apart. It transforms the universe's greatest challenge, the relentless and relative flow of time, into our most beautiful opportunity for connection. This technology's promise extends far beyond the cold calculus of preventing spaceship collisions or streamlining financial logs. Its true power lies in its ability to foster a genuine cultural and psychological unity. Imagine a future where a child gazing at the pale, tiny dot of Earth from a dome on Europa doesn't feel a pang of loneliness but a sense of shared presence. Because they know that at that very moment their cousin back on Earth is also looking up at Jupiter, and both of their clocks agree, down to the picosecond, that it is precisely the same instant in human history. This shared now becomes a powerful antidote to the existential isolation of space, a constant, silent reassurance that we are not a scattering of lonely outposts, but a single civilization experiencing the same unfolding moment together. It provides the temporal foundation upon which shared experiences, solar system-wide broadcasts, simultaneous memorials, real-time collaborative art can be built, nurturing a common identity that transcends planetary boundaries. As we stand on the precipice of this new era, looking out at the star-dusted darkness that we are poised to fill, the path forward is clear. It will not be paved by a single nation or corporation in isolation. The magnitude of this undertaking demands a collective spirit of collaboration and curiosity, unlike any we have mustered before. It requires physicists and engineers to push the boundaries of the possible, diplomats and lawmakers to craft frameworks of shared governance, and artists and storytellers to help us all envision the profound human connections this technology will enable. It calls on the dreamer in all of us to support the ambition to become more than what we are, to reach out not as competing factions, but as a unified species, synchronized not just in time, but in purpose. The journey to this future begins with a conversation, right here, right now. We want to hear your vision. How do you imagine synchronized time will change the experience of living off Earth? Will it make the cosmos feel smaller, more manageable, or will it open up even grander possibilities we haven't yet dreamed of? Share your thoughts and ideas in the comments below. Let's explore this future together. And if you want to join us for more deep dives into the technologies that are reshaping our world and our place in the universe, be sure to subscribe and hit the notification bell so you don't miss what's